This spark, this little spark, from the smallest of neuron firing in our brains that gives us wonder and hope, to the cosmic collision of two black holes that holds us together in space and in time. We are connected by this collective spark for knowledge, for purpose, and understanding. It is reflected in the systems we build, the connections we make, the science we produce. We are HPC. Challenges that were once thought to be too vexing and intractable are proving solvable through the power of HPC. Our community is creating breathtaking breakthroughs where only a few decades ago stood seemingly impenetrable walls. We are now connected and collaborative in an unprecedented global scale, working together with new data, new technology, and new purpose. We're here to kindle that spark, to imagine what could be. Welcome to SC17. Please welcome Bernd Mohr, SC17 General Chair, Jülich Supercomputing Center.
Hello world, or should I say hello HPC world? I welcome everybody to the great city of Denver for the 30th annual SC conference. In 1858, gold was first discovered only 5 miles from this very spot, an event that led to the founding of our host city Denver, as well as to the great Rocky Mountain Gold Rush, which is fitting, because today, high-performance computing is at the forefront of a new type of gold rush, a rush to discovery using an ever-growing flood of information and data. Computing is now essential to science discovery like never before. We are the modern pioneers pushing the boundaries of science for the betterment of society. And while we find ourselves here in Denver, smack dab in the middle of North America, SC continues to expand its international attendance and participation. This year, the world truly has come to Denver. It's an international conference with over 2,800 international attendees from 71 countries, including over 122 international exhibitors bringing product innovation from around the world. 21% of our workshop organizers and tutorial speakers are from outside the US, as are 22% of our technical paper authors. And our 153 volunteers, student volunteers, congregate from every continent of the globe except Antarctica. And I assure you, we're working on that. Any volunteers? This international shift is reflective of the direction of science and research. We are no longer lone scientists at our home organizations. Our community now runs experiments in massive global collaborations. This paradigm requires us to bring together geographically distributed computing systems, scientific instruments, and the brilliant minds of our community in an unprecedented way. We are already seeing the results, from an accelerated discoveries in basic research to the development of new markets and industry, leading to new economic opportunities. The fact that 12,000 of our closest friends are all here together in Denver says that SC has become an incredible connection point for our community. Coming from every part of the globe, to sitting here in this audience, joining us for the whole conference, we have some of the greatest scientific experts of our generation alongside emerging leaders of tomorrow. The conversations of our sessions in the hallways of this awesome convention center and across our massive exhibit floor every year lead to new partnerships, and I'm glad to say also lifelong friendships. These connections are needed to tackle so many challenges that we can't just possibly do alone. For instance, what is it that makes us human? The Human Brain Project is a scientific collaboration including hundreds of scientists, 5 supercomputers, and 24 countries. I'm so proud that my own organization, Jülich Supercomputing Center, is part of this. The project will span a full decade and has already engaged physicists, neuroscientists, psychologists, and computer scientists working together to develop a never-before-imagined map or atlas of a human brain, right down to the molecular level. This project will require the storage and analysis of vast amounts of data and arrays of supercomputing power. Scientists will be able to use these models to make dramatic progress in preventing and curing serious diseases that affect our friends and family, like brain cancer, CET, Alzheimer's, and other disorders. Oops. From the tiny molecules of our brains to the farthest reaches of our universe, our community is making a big impact. As I'm sure everyone here in the room knows, just last month, the leaders of the Laser Interferometer Gravitational Wave Observatory, or LIGO project, actually got awarded the 2017 Nobel Prize for Physics. In what the Academy described as a discovery that shook the world, LIGO scientists detected 4 cosmic chirps, or gravitational waves originating from the collision of black holes 1 to 3 billion years ago, a discovery which was first theorized by Albert Einstein in 1916. Using billions of bits and bytes of observational data, scientists used the power of HPC to find this very same signal, and they got the prize for that. One of the Nobel Prize winners commented that LIGO's success was made possible through 40 years of working involving thousands of hours of thousands of scientists around the world. And from this effort will spring a new field of astronomy, from which a treasure of new discoveries will come. Computation is not the only piece of a technology puzzle. We need networks, very fast networks and well-tuned networks to actually connect researchers to their data, to computing resources, to experiments, wherever they may be in the world, or even here at the conference. And that's why every year the SC conference builds SciNet, the fastest, most powerful network in the world. One that last year peaked at transmitting over 3.3 terabits of data per second, and this year we hope that even get some more. SciNet is a marvel. It takes a full year to plan, 3 weeks to set up, 1 week to operate, and then we tear it down in just 1 day. SciNet is operating with over 66 million in loaned state-of-the-art equipment and software. I would like to thank our top SciNet contributor organizations for giving us all that stuff. Thank you. Thank you. And most importantly, I want to thank all of the 175 volunteers from higher education, government agencies, as well as partners from industry to make this grand effort possible. Actually, if you have some time during the week, I invite you to check out SciNet's impressive class-encased network operating center on the exhibit floor just above us, to see all of your bits and bytes, or should I better say terabits and bytes, in action. As you know, the challenges in our industry are not just scientific or technological. They are also societal and demographic in nature. As you may know, just look at me, 80% in our field are male and 80% are white. This is something we are addressing with urgency. And not just because of moral or ethical reasons, for that should be enough, but also for pragmatic and business reasons. Currently, there are approximately 250,000 computing jobs that go unfilled each year in the US alone, and the same trend is true in the whole world. That number is expected to grow to over 1 million by 2022. We are an industry in desperate need of new talent, of as many brilliant minds as we can marshal, who are excited to push the boundaries of science. And where will these future colleagues come from? Hopefully not from a narrow democratic band of the past. We must do so as much as we can to reach out to underrepresented groups so they feel inspired to join our industry, not in mere trickles, but in a sure and steady flow. Our community is in the business of collaboration. Collaboration is the essence and foundation of science because we require so many different perspectives to solve even the smallest of our puzzles. How can we consider ourselves truly collaborative if we are not fully inclusive? To address these challenges, SC has launched a number of programs that we hope will lead to change and will expand our HPC workforce. For the second year, we are offering on-site childcare at SC17 so parents can be supported and encouraged to advance their professional development. We began this program last year and have more than tripled the number of children participating in the program this year. Thank you. On another front, we will again announce the winners of the Computational and Data Science Fellowships on Thursday in this very same room. This program, generously supported by ACM, SIG HPC, and Intel, is designed to boost the number of women and minorities who pursue graduate degrees in this field. And for the third year, we host the Women in IT Networking at SC17, or WINS, a program supported by the Department of Energy and the National Science Foundation. Designed to enhance and accelerate the careers of female network engineers by funding 5 emerging leaders to be part of our awesome SciNet effort. Finally, I want to highlight the new SC Inclusivity Travel Grant, which supports promising early career professionals from organizations and countries where HPC is just starting to become an important factor for research and business. And to those who may not otherwise be able to attend, but who have demonstrated that they can provide considerable value to the HPC community. This year, our first winner comes from all the way from Nepal in the Himalaya to us to the conference. Thank you. Yeah. These are just a few of our endeavors on this important front, the success of which is crucial to our future. I have spoken a great deal about the importance of collaboration. And I can proudly say that this spirit of collaboration is remarkably evident among the over 600 volunteers from around the world who have worked tirelessly over the past 2 years to make SC17 happen. For those that may not know, every facet of this conference, not just the technical program, is planned by our peers who, with the support of their home organizations, government labs, universities, corporate partners, give up their time to make this all possible. Anything from the science you see around in the convention center, to catering, to the registration process, whatever, to our awesome keynote that you see this morning, it is all planned by 600 people in our community. If you're one of these selfless heroes, please stand up to be recognized. Thank you guys, you did an awesome job. We can't honor the new future of science we envision without honoring the pioneers who led us here. It's our tradition to honor 2 distinguished members of our community whose contributions have made a long-lasting mark in HPC. Here to present our 2 distinguished ACM and IEEE awards, please welcome the 2017 ACM Vice President Sherry Pancake and the 2017 IEEE CS President Jean-Luc Godieu.
Thank you, Bernd. It's an honor to be here today to recognize 2 individuals who have distinguished themselves as truly extraordinary in their accomplishments and contributions to high-performance computing.
Our first award of the morning is the ACM IEEE Computer Society Ken Kennedy Award.
The ACM IEEE Computer Society Ken Kennedy Award honors outstanding contributions to programmability or productivity in high-performance computing, together with significant community service or mentoring contributions. This award was established in memory of Ken Kennedy, the founder of Rice University's nationally ranked computer science program, and includes a $5,000 honorarium. The 2017 ACM IEEE Computer Society Ken Kennedy Award is presented to Professor Jesus Labarta of Barcelona Computing Center. For more than 35 years of his academic career, Professor Labarta has made significant contributions in programming models and performance analysis tools for parallel, multi-core, and accelerated systems. His main objectives have been to help application programmers to improve their understanding of their application's performance and programming productivity for very large-scale systems. His research team has been developing performance analysis and prediction tools named Parivar and Demimus, and pioneering research on how to increase the intelligence embedded in these performance tools. He has also inspired the vision for the task-based stars programming model, behind the scenes giving the runtime system the required intelligence to dynamically exploit potential parallelism and resources available. His team has influenced the evolution of the OpenMP standard with OMP's instantiation of stars, and in particular its tasking model. In the spirit of Ken Kennedy, Professor Labarta has had long-term commitment to mentoring junior researchers.
Ladies and gentlemen, please help me welcome the 2017 ACM IEEE CS Ken Kennedy Award recipient, Jesus Labarta. Congratulations.
Our next award is the IEEE Computer Society Sidney Fernbach Award.
The IEEE Computer Society Sidney Fernbach Award honors the memory of one of the pioneers in high-performance computers. Established in 1992, the award and $2,000 honorarium are given to an individual in recognition of outstanding contributions in the application of high-performance computers using innovative approaches. The 2017 IEEE Computer Society Sidney Fernbach Award is presented to Dr. Stephen J. Plimpton of Sandia National Laboratories. Dr. Plimpton's research has been primarily focused on methods and parallel algorithms for a variety of particle-based HPC applications. Along the way, he contributed to a few combinatorial algorithms for problems like contact detection and radiation transport. He is best known for leading the development of open-source codes used for modeling materials at different scales. These include LAMPS, software for running classical molecular dynamics simulation, SPARCS, Monte Carlo modeling of materials processing at the mesoscale, and SPARTA, DSMC modeling of turbulence and flow in low-density gases. The most widely used of these is LAMPS, which is a worldwide community of thousands of users and hundreds of code contributors. He has also worked on MPI-based tools for big data processing on HPC platforms, including MapReduce and stream processing libraries. Dr. Plimpton's contribution in the field of large-scale computing simulation codes have become essential tools for large research communities and have enabled scientific advances in multiple research disciplines.
Colleagues, friends, please help me congratulate the 2017 IEEE Computer Society Sidney Fernbach Award.
And before I introduce our keynote speakers, I would like to highlight a special session that we are holding with another HPC. Gordon Bell, whose breakthrough work has led many to call him the father of a mini-computer. We are honored to have him at our event, and I encourage you to take part in his session today at 3:30 p.m. just here in this ballroom. Now again, I turn to the heavens, or more specifically to one of the most ambitious projects in the history of astronomy. I am referring to our keynote presentation on the Square Kilometre Array, a massive multi-site radio telescope project slated for construction in South Africa and Australia. When operational, SKA will provide humankind with answers to fundamental questions about the origin and evolution of the universe. Your innovations are part of that fabric that make this massive science instrument possible. Two leaders of this breathtakingly project are here today to wow and inspire you. I bring you Phil Diamond and Rosie Bolden.
SC17 Keynote speakers Phil Diamond and Rosie Bolton are leaders in the development of the Square Kilometre Array, which when completed will be the world's largest and most sensitive set of radio telescopes distributed around the world. As Director General of the SKA organization, Professor Phil Diamond is responsible for the team designing and ultimately constructing SKA. Phil has 30 years of experience in the field of radio astronomy and was part of the early leadership of the SKA collaboration. Dr. Rosie Bolton is the SKA Regional Center project scientist as well as the project scientist for the International Engineering Consortium, designing the high-performance computers that will analyze the anticipated 300 petabytes of data per year of initial science data produced from SKA's instruments. Please welcome to the stage Phil Diamond and Rosie Bolton.
Good morning. We're delighted to be here with you today to tell you our story, the story of the Square Kilometre Array, or the SKA for short.
As you know, the theme of the conference this year is HPC Connects, and we're going to spend the next 40 minutes or so showing you all why the SKA is such a fitting example. SKA is an exascale science project that will push forward the boundaries of scientific endeavour and engineering capability for decades to come.
To explain how this will happen, we're going to take you on a journey. And just like any scientific adventure, our journey starts with some questions.
What did the universe look like when the first galaxies formed?
What are gravitational waves? How does magnetism work throughout the universe?
Come si formano I pianeti?
How many gravitational waves are passing through me right now?
What is dark matter?
What is the impact of magnetic fields on the formation of galaxies?
宇宙の歴史はどうだったか?
¿Estaba Einstein en lo correcto?
And for me, the most important is there life out there?
We ask ourselves, what is the most useful thing that a radio telescope can contribute to the answers to these big questions? We are building a time machine. We're looking at what our surroundings were like almost at their inception. The question is, how are we actually going to make this happen?
Astronomers are experimental scientists, just like chemists, biologists, and physicists. Except that our experiment is already running, and we forgot to write down the initial conditions in our notebook.
Our experiment, of course, is the universe. And unlike lab scientists, we can't repeat it to see what happens if we change a variable. So instead, we watch it very closely and try to understand what those initial conditions were and what the laws are that have shaped its evolution. Until very recently, the only messenger for this information was light, or electromagnetic radiation. The pioneers of astronomy used only one aspect of light, and that was optical light, which is just one portion of what we call the electromagnetic spectrum.
Perhaps the most famous pioneer of optical astronomy was the Italian polymath Galileo Galilei, who spotted the 4 largest moons of Jupiter with his own instrument, an optical refractor. Although that might not sound very fundamental to us today, this discovery was a complete revelation. Galileo, with his telescope, had proven not only that objects existed in the heavens, beyond those that we could see with our own eyes, but also that there were celestial objects other than our Earth that had orbiting bodies.
The electromagnetic spectrum itself is vast. Optical light that we see with our human eyes, with all of its beautiful colors, occupies just a tiny region somewhere in the middle. Far over to your right are high-energy photons, gamma rays, and then moving left, we get to X-rays, and then down into ultraviolet, which is still energetic enough to give us sunburn before we even reach optical light. Just below the visible light in energy is infrared, which is the cozy radiation we feel sitting by the fire. And then past infrared, we make the transition into microwaves. And then finally, where each photon has energy 1 million times less than that of optical light, we get to radio wavelengths.
To study each of these wavelengths, we have developed powerful instruments. Each of these has allowed us to unravel, piece by piece, the mysteries of our universe, starting with the visible part of the spectrum. Technology has somewhat evolved over the last 400 years since Galileo, and nowadays optical telescopes are bigger and better, some measuring several meters in diameter. Some names will probably ring a bell to most of you, like the Hubble Space Telescope, the twin Keck telescopes in Hawaii, and the European Very Large Telescope in Chile. All of these have enabled us to discover a sky filled with faraway galaxies and to observe the expansion of the universe, amongst many other highlights. We are now entering the era of extremely large telescopes with mirrors measuring several tens of meters in diameter, almost as wide as the screen you see behind us here.
But moving away from optical, at the high end of the spectrum, gamma-ray telescopes like NASA's Fermi have revealed the most powerful explosions in the universe, namely gamma-ray bursts. These are believed to be extremely energetic explosions that occur when a high-mass star dies in a supernova, forming a neutron star or a black hole. And in the next few years, the soon-to-be-built ground-based Cherenkov telescope array instrument should provide more insights about this important part of the spectrum. Moving leftwards, we find the X-ray space telescopes, such as the European XMM Newton or the American Chandra, which provided spectacular photos of star clusters and collisions between clusters of galaxies. Chandra has also helped to confirm that the galaxies and the universe are mostly made up of stuff that we can't see, dark matter and dark energy, but a bit more on that later.
In ultraviolet astronomy, an example is the European Solar and Heliospheric Observatory, SOHO, which helped us get a much better understanding of a star which is very familiar to us all, our own sun, by studying its outer layers as well as the solar wind. Then, on the other side of visible light, we find infrared. Infrared astronomy is the study of the cold universe, those regions made of molecular gas and dust which block the visible light, but which emit and are transparent in infrared. Infrared instruments such as Spitzer or Herschel, and more recently the airborne observatory SOFIA, a telescope in a 747, contributed significantly to our understanding of the universe by peering into these cold, dark regions where stars and planets are formed. And just 18 months from now, the replacement to Hubble will be launched, the James Webb Space Telescope, a revolutionary instrument developed jointly by the US and Europe.
Moving further left on the spectrum, we find microwave telescopes such as Planck. Planck is famous for mapping the cosmic microwave background, or CMB, in exquisite detail. The discovery of the CMB was probably one of the most fantastic astronomical developments of the last century, since it represents radiation left over from the earliest time in the universe and is evidence of the Big Bang. Its discovery in 1964 by radio astronomers won the Nobel Prize.
So, each of these facilities has allowed us to look through a small window into the universe and put together one more piece of the puzzle. Used together, they have opened up huge swathes of knowledge to us all. But of course, there's one window we haven't yet talked about, which is probably the most interesting part of the spectrum. I do hope there are no non-radio astronomers in the room. It's the radio window, which has already allowed us to unravel many mysteries of our universe and which should help us add many more pieces to the overall puzzle.
Radio astronomy is a relatively recent branch of astronomy. The first radio antenna pointed at the sky was built by American physicist and radio engineer Carl Jansky in 1931 as he was working for Bell Labs. He was trying to find the cause of persisting interference on radio communications. And sure enough, he found a hiss that rose and set every day, shifting by 4 minutes each time. Now that shift is a big clue to astronomers. It tells us that the cause is not linked to the daily rhythms of the Earth, but to the sky beyond, shifting with the seasons as the constellations do. In fact, Jansky had just discovered radio waves emanating from the Milky Way itself. The optical astronomy establishment largely ignored Jansky's discovery. However, in 1937, an amateur astronomer and radio engineer, Grote Reber, was intrigued, and he built his own radio telescope in his backyard in Illinois. And with this homemade antenna, he mapped new objects in the sky that shone brightly in radio waves, and yet were almost invisible at other wavelengths. Now, these hand-drawn contour plots might look crude to us nowadays, but this was exceptionally good science. They're actually the first radio contour maps of the galaxy. Reber was a remarkable man. For a decade, he was the only radio astronomer in the world. That must have been a very lonely existence.
There's a few more of us now. In the 1940s, actually during the Second World War, Dutch astronomers predicted neutral hydrogen would emit a radio wave with a wavelength of about 21 centimeters, a frequency of 1420 megahertz. Its later detection marked a critical milestone in radio astronomy. Hydrogen atoms are the simplest atoms possible. They have one proton and one electron. But then quantum mechanics comes into play. Protons and electrons are both quantum objects, and they have a quantity called spin. It turns out there's a tiny difference in energy for a scenario where the electron spin and the proton spin are parallel compared to when they are anti-parallel. This spin flip, as we call it, from the higher energy state to the lower energy state happens spontaneously, but not very often. Only about once per 10 million years per atom. But there are a lot of hydrogen atoms. It's the most common element in the universe. And when this spin flip does happen, the atom releases the spare energy as a photon, giving radiation at precisely 1420 megahertz. So what? While this emission occurs at a precise frequency, this frequency will change if the atom is moving towards you or away from you, as you see in this little animation. It's the exact same phenomenon that occurs when a speeding police car comes your way or is moving away from you. This is called the Doppler effect. Did you hear that? Stop, let's hear that one again. They're not coming to take us away, but that is that's an example of the Doppler effect. So if the gas is moving away from us, it's occurring at a lower frequency. It is redshifted. If it's moving towards us, it's blue shifted. But when it's redshifted, its signal literally shifts towards the lower frequency part of the spectrum. There are two main contributors to redshift, well, to this Doppler effect. Dynamics within a galaxy will give a shift, as you see on the screen behind us. Galaxies are rotating objects, and observations of their hydrogen emission reveal this motion, with one part of the galaxy moving towards us and the other moving away.
But more famously and more importantly for exploring the structure in the universe, we have cosmological redshift. Now this arises from the motion away from us caused by the expansion of the universe. So every distance between objects is increasing. And as the web of the universe expands, we see the light from galaxies redshifted to lower energies. The further away a galaxy is, the faster it's receding from us, and the bigger the shift in the spectrum from that galaxy. So if you can measure the cosmological redshift of a galaxy, it tells you how far away the galaxy is from us. So why is radio special? Well, the universe is full of dust. That's clumps of icy, sooty debris floating in space. And this dust blocks the optical light, as you can see in the Milky Way here. But radio waves can pass straight through. So if we use radio light, the scope of our experiments is only limited by the dimming of emission as objects are further away from us. If we build a sensitive enough radio telescope and measure down to low enough frequencies, we can detect hydrogen from very early in the universe. If you can detect the hydrogen and measure its frequency shift, you can map the universe, not in 2 dimensions, but in 3D. This is a core concept for the SKA, which we'll come back to later.
In 1957, Sir Bernard Lovell built the 250-foot diameter telescope at Jodrell Bank near Manchester in the UK. And that's where we are located. There's some archived Pathé footage here that was filmed to promote Jodrell Bank at that time. I think it's absolutely fantastic.
At Jodrell Bank, Cheshire, the greatest radio telescope in the world is nearing completion. A giant with 2,000 tons of moving parts, surmounted by a reflecting bowl 250 feet across. The object of the bowl? To concentrate radio waves from outer space, so that radiations which have been traveling for millions of years at the speed of light can be detected, measured, and analyzed. To do that, the bowl can be pointed accurately in any direction, even in a high wind. In charge of the station is Professor A.C.B. Lovell, on the right. Mr. H.C. Husband designed the telescope, which is operated from a control building. Like many great research centers, it's a university project, in this case, Manchester.
Note the strong adherence to health and safety back then. The Lovell telescope, now named after Sir Bernard, became the world's biggest telescope, radio telescope for 14 years and played a major role during the space race in the 60s. But more importantly, from a scientific point of view, in the study of a new class of objects called pulsars. Pulsars are very fast spinning neutron stars, dead stars essentially, rotating many times a second. They emit beams of radio light from their magnetic poles. If these beams are aligned towards the Earth, for some parts of their spin cycle, we see regular blips, like a cosmic lighthouse, basically. Pulsars are extreme objects. They are test beds for some highly unusual physics, but they are also useful as probes for different phenomena. More on that in a moment. Other large facilities were also developed around that time. In the 1960s, Cornell University built the Arecibo telescope, a 305-meter diameter instrument in a sinkhole in Puerto Rico. The one you may have seen James Bond sliding down into if you're old enough. Until recently, it was the largest single dish pointing at the sky, until the inauguration of the 500-meter diameter FAST telescope in China last year. A true monster, which I had the pleasure to visit. It's really a mind-blowing project. That antenna has a 1-mile circumference. It's really huge. Now, in parallel to the development of large single dishes, the technique of interferometry, superimposing waves effectively, was first developed in Cambridge. Not your Cambridge, ours in the UK, and for use in radio astronomy. It uses a technique we call aperture synthesis, using the Earth's rotation and combining signals from multiple telescopes to act like one giant telescope. That technique, together with the discovery of pulsars, won a Nobel Prize in 1974.
Well, let's stop here for a second to explain this a little bit more. To build a better radio telescope, you could, in theory, simply build bigger and bigger radio dishes. But you can see from this photo what could potentially happen.
This actually happened in 1988 in Greenbank, West Virginia. And actually, I know the guy who was the duty operator on the telescope that night. He says, surprisingly, that his supervisor didn't believe him when he called late at night to tell him the telescope had disappeared. The National Enquirer, one of your quality newspapers, blamed aliens. It was actually metal fatigue.
So you can see that potentially building bigger and bigger either becomes technologically very hard, or you risk your telescope turning into a giant pretzel, or very expensive. And there aren't handy sinkholes located around the world everywhere where we might potentially want to build a radio telescope. So there are 2 key performance measures we can think of when we consider telescopes, and they are their resolution and their sensitivity. Resolution is the ability to detect finer detail on the sky. For an interferometer, this is determined by the largest separation between any pairing of antennas. Build antennas further apart, and you get information on smaller spatial scales. So you can make finer pixels in your map. It's like a zoom lens, basically. Sensitivity, on the other hand, depends on the total amount of collecting area. Basically, how many radio photons we can gather up. So adding more dishes improves sensitivity, and we can see fainter details. That means weaker objects, or objects further away, and therefore further back in time in the universe. So since the invention of aperture synthesis, use of the arrays of telescope has boomed.
A famous example of a major facility using aperture synthesis is the iconic Very Large Array, a 27 antenna array in Socorro, New Mexico, effectively just down the road. Built by the US National Radio Astronomy Observatory in 1973, it's currently the state-of-the-art in radio astronomy. I worked there in the desert for 10 years. You may have seen Jodie Foster using it as well and listening to alien signals with her headphones on in the movie Contact, which is a classic movie for us radio astronomers. Building on this technique further, in the late 2000s, North America, Europe, and East Asia joined forces to build ALMA, the Atacama Large Millimeter Array, at 5,000 meters altitude in the Chilean Andes. With its 66 dishes spread over 14 kilometers, it is currently the largest array of radio telescopes in the world.
Yeah, ALMA is a fantastic instrument and a great example of international collaboration. One of its scientific goals is to observe protoplanetary disks, that is, planets forming around other stars. On this ALMA image of the nearby star TW Hydrae, we can see the disk of debris orbiting the star. This disk has some characteristic circular gaps in it, which we believe are caused by planets on those circular orbits gobbling up the debris in their path. Now, the blobby zoom in the center here shows another gap very close to that star. And that's very significant because the distance between this gap and the star is the same as the distance between us and the sun. So we could be here witnessing the birth of Earth's twin. So we've gone from Jansky's simple aerial and Reber's backyard detector to ALMA's array of dishes in just 80 years. That's quite an impressive rate of development. These radio telescopes tell a story of increasing complexity. Each new telescope is bigger, better, and can see in more detail and peer deeper into the cosmos than its predecessors.
We've made many major discoveries, but one important chapter in our book of the universe is still missing and can be summarized in one question. What did the universe look like when the first galaxies formed? With Planck, we mapped the cosmic microwave background. That is a snapshot of what the universe looked like some 380,000 years after the Big Bang. But what happens after that is still a mystery to us. We call this time in the universe's development the Dark Ages. For roughly 150 to 400 million years, we see nothing. There is nothing except a soup of neutral hydrogen. Gravity then pulled matter together in ever denser clumps until eventually the first stars formed, and then the first galaxies. Those first stars radiated energy that ionized the neutral hydrogen, stripping the atoms of their electrons. No electron, no spin flip. No spin flip, no radio emission line. So, in theory, if we look back in time by looking far away and at high redshift, and watch what happens to the neutral hydrogen as the universe ages, we should see this emission dying away as more and more stars shine and holes will be burnt into the soup of hydrogen, something like a Swiss cheese, until the hydrogen is almost all reionized. It is this that originally led us to the concept of the square kilometer array back in the early 1990s. Scientists came up with this concept for a so-called hydrogen array, a telescope that would be sensitive enough to detect the signals from the dark ages of the universe, 13 billion years ago. To do this, we estimated the telescope would need to have a square kilometer of collecting area, and that's how the SKA was born. But of course, with a telescope of that size, you can also study many other things.
Magnetism is one of them. Magnetic fields play an important role throughout the universe on scales as small as centimeters and as large as 1 billion light years. With the SKA, we hope to address the challenge of explaining how and when magnetic fields arose and evolved to achieve their current strength. We will produce the first three-dimensional magnetic map of the universe. Dark matter and dark energy are huge ongoing mysteries, as we mentioned earlier. We plan to play a role in tackling them and providing answers by studying galaxy evolution. Even in its early deployment phase, the SKA will be able to map 10 million galaxies spanning 8 billion years of evolution. And when the full SKA is deployed, we'll conduct the most complete galaxy census ever contemplated in 3D, encompassing up to 1 billion individual galaxies and covering 12.5 billion years of cosmic history. From these data, astronomers will be able to make the most precise determination yet of the properties of dark energy driving the expansion of the universe.
Another open question is that of how planets formed. Rosie told you a moment ago how ALMA addresses one part of this, but we still need to understand how the small pebbles in the disk surrounding a young star are able to stick together to form the boulders that ultimately coalesce into planets. With the SKA, we'll be able to observe coalescing particles from centimeter to meter scales, complementing ALMA's work, and eventually to watch in real time the formation of planets much like our own.
And then there is, of course, the eternal question of whether or not we're alone in the universe, and whether it's possible to detect the presence of technologically active civilizations elsewhere in our galaxy. We call that SETI, the search for extraterrestrial intelligence, and that's something that we'll be uniquely able to address with SKA. For the first time, we'll be able to detect emissions from planets around nearby stars, comparable in strength to the signals that we generate with our human activity on Earth.
SKA will also contribute hugely to the nascent field of gravitational wave astronomy. Gravitational waves have been in the headlines, as Bernd said earlier, for the past couple of years, since their first detection by LIGO in the US and the European equivalent Virgo just very recently. Most recently, the groundbreaking follow-up to the fourth gravitational wave event, using a whole range of different telescopes around the Earth, is enabling us to understand the nature of the sources that generate the gravitational waves. We have many questions. What are they? What characterizes them? And we're finally beginning to get answers. But how can the SKA detect gravitational waves, you might ask?
Well, the key is in the pulsars. So far, we know of a couple of thousand pulsars. But with the SKA, we'll have the sensitivity to detect all of the pulsars in our galaxy that are pointed towards us, which is many times more than we currently have. Now, some of these will spin extremely fast, hundreds of times per second, and for a few dozen, we'll be able to use them as clocks, more accurate than our best atomic clocks. In this animation, we represent two such pulsars. When a gravitational wave passes through the galaxy, it will cause a ripple in the fabric of space-time. As these ripples pass by, the distance between the pulsar and us on Earth changes slightly. They get closer or further away. And those pulsar signals, which we should be able to set our watches by, arrive a little early or a little late. Measure that time shift, and you've detected a gravitational wave passing through. If you use a whole collection of these pulsars scattered across the galaxy, you've got yourself a galactic-scale gravitational wave telescope. It sounds like science fiction, only it isn't.
All of the science we've just described is captured in the science case for the SKA. We published the revised version 2 years ago. More than 1,300 authors from around the world contributed some 100 papers in 2,000 pages. It's in 2 volumes, as you see on the screen behind us, because the printer couldn't bind more than 1,000 pages together. Together, they weigh 10 kilograms. So that's your carry-on luggage right there. And by the way, you're all getting a free copy in your conference bag.
So 24 years after the initial concept, the SKA is an international project currently funded by 10 countries and bringing together over 1,000 engineers and scientists from 270 institutions across 20 countries. 24 years might sound like a lot, but timelines to develop these mega science projects, such as ALMA and the extremely large telescopes that we showed earlier, or for space missions, really are now measured in decades because of their very nature. For the SKA, the collaboration spans the globe across 20 time zones. In the SKA project, the sun truly never sets.
We also need close partnerships with industry to develop the technologies we need. We must work closely with policymakers to ensure that the facilities we build fit into the country's research strategies. Governments and decision makers need lots of political will to go beyond the re-election cycles and fund these infrastructures over these long periods of time. At a diplomatic level also, governments must agree to work together for their mutual benefit, sharing the burden of funding these facilities. And of course, we, within the project, must work with our local communities to ensure that they also benefit from having such infrastructures next door. Simply put, such facilities cannot be done by any single country anymore.
Our headquarters, currently under construction, is located at the iconic Jodrell Bank Observatory that we mentioned earlier, and that's contributed so much to the field. And actually, because of that contribution, the observatory has been shortlisted to become a UNESCO World Heritage Site. So it's a very fitting place for the home of what will be the world's biggest radio observatory. This is a 250-foot level telescope today, and our office is under construction in its shadow, and some cows and sheep alongside for good measure.
It's really a lovely place to work. So our funding, we have committed 200 million euros for design, and a large fraction of the 674 million euros required for construction of the first phase of the SKA. This is all provided directly from government research budgets. In fact, in order to ensure the stability of the facility over its planned 50 or more years of operation, we are creating a new intergovernmental organization to run the observatory, something like CERN or the European Space Agency. We're now very close to having this process finalized, and we expect our member countries to sign the text of the treaty in Rome early next year. You can actually see a photograph here of the country representatives during one of the negotiation meetings, which have all taken place in Rome.
On the science front, we have 12 science working groups composed of researchers from the astronomy community, studying some of today's hottest questions in astrophysics and how to answer them with the SKA. Their work focuses on refining the kind of observations we'll conduct and how many hours we believe will be needed and what we expect to find. These researchers are also very active using the current state-of-the-art facilities as well. Because SKA, of course, is not being invented from scratch. It's being built on the shoulders of giants, making the most of what we've learned so far. These giants obviously include the VLA and ALMA, but also others like the LOFAR array spread across Europe and GMRT in India, which was recently used to track the descent of a European Space Agency lander on Mars. We also have prototypes on site, testing promising technologies and providing insight on local conditions. These include the South African-built Meerkat array, whose 64th and final dish was installed last month, and the Australian SKA Pathfinder ASCAP, which is now being commissioned, equipped with 36 dishes and novel receivers that act like radio cameras. An interesting fact is that our colleagues there have built renewable energy solutions to power the observatory, and as of the end of last week, the site of the telescope is now powered by a 1.6 megawatt solar farm, which is paving the way for the use of renewable energy for the future SKA. At the SKA sites, there's also 2 international collaborations between universities which include those in the US, the Murchison Wide Field Array in Australia and the Hydrogen Epoch of Reionization Array in South Africa, searching for that telltale hydrogen signal from when the first stars formed that we saw earlier. So we're really building on a huge amount of work internationally. The SKA is the culmination of 80 years of radio astronomy engineering development.
Concerning that engineering development, we have 12 international consortia, you see them on the screen there, which bring together 100 of the world's top institutes and companies to design the telescope, based on the requirement developed by the astronomers. The consortia each focus on a key aspect of the telescope, such as signal and data transport, the software needed to operate the telescope, the computing, the receivers with which the telescope and antennas will be equipped, etc. Over the past 4 years, they have been busy designing and refining the telescope and all of its subsystems, based on the best available, most reliable, cost-effective technology, and inventing new technologies. They're heading to full steam towards critical design reviews next year. And for those of you familiar with project management and systems engineering, you know this is when the light becomes visible at the end of the tunnel. Been a huge amount of progress in the past few years, and a lot of activity happening all over the world. And in just this past year, we've seen major progress to manufacture, install, and test the future antennas of the SKA. As you can see here on the screen, there's already metal on the ground. On your left, you see a video taken a few weeks ago showing 2 prototype dishes being manufactured at a factory near Beijing in China. And then on your right, a lovely video showing the transportation and construction of the prototype low-frequency antenna array in Australia. Such prototypes are essential as we test and refine our designs before full construction starts just 2 years from now. So, what are we actually building, you might ask? Well, all of this work by thousands of people over the past 20-odd years has been leading up to this. 2 telescopes, one in South Africa and one in Australia, in 2 very remote regions of the Earth. Our sites are in the Karoo, 600 kilometers north of Cape Town, and the Murchison Shire, 800 kilometers north of Perth in Western Australia. On the screen, you will see animations of what I hope you will see over the next few years, antennas flowering in the desert. In South Africa, we're going to be building close to 200 dishes, each of them 15 meters in diameter, and the dishes will be spread over 150 kilometers. For the geeks amongst you, and there may be 1 or 2 in the audience, the dishes are actually offset Cassegrains with an aluminium surface and a composite subreflector. They're going to be operating over a frequency range of 350 megahertz to 14 gigahertz, and will almost certainly work at higher frequencies. In Australia, we will build 512 clusters, each of 256 antennas. That means a total of over 130,000 2-meter-tall antennas spread over 65 kilometers. These low-frequency antennas will be tapered log-periodic dipoles. They will cover the frequency range 50 to 350 megahertz. It is this array that will be the time machine that observes hydrogen all the way back to the dawn of the universe. And by the way, the reason we have to develop 2 different types of antennas is just because in optical astronomy, a 3rd technology, the mirrors, is used to capture visible light. We need different technologies to capture the different wavelengths of radio.
And why so remote, you might ask? Well, this is why. To get away from the artificially generated interference. So you may all be familiar with light pollution, the glow of a major city, even from miles away, that prevents you from seeing the stars in the sky. Well, radio pollution is similar. It's the noise generated by all of our electrical equipment, mobile phones, Wi-Fi, etc. And it swamps those really faint radio signals that we're trying to receive from the sky. So we have to get away from civilization to be able to do the best science. It's a touch ironic, really, because it was radio astronomy developments that led to the invention of Wi-Fi. So we have rather shot ourselves in the foot there.
But this first phase represents only a small fraction of what we hope to build. Eventually, we plan to have up to 2,000 dishes spread over southern Africa, stretching into Namibia, Botswana, Mozambique, Madagascar, Mauritius, Zambia, and all the way up to Ghana in Kenya. And in Western Australia, we expect to build up to 500,000 antennas spread across the desert. It really looks beautiful, doesn't it? Even phase 1 of the SKA is a real game changer in terms of capability. Consider this. Here's a comparison of the collecting areas between the SKA phase 1 telescopes and the current state of the art. The Dutch LOFAR telescopes at low frequencies, and the VLA, the Jansky VLA, at higher frequencies. And here's where we fit in with our first phase of construction. So we're not incremental, we're actually skipping a whole generation of telescopes. These images you see on the right of each of those sections there illustrate just how much better the SKA will be at imaging complex objects on the skies. These are currently simulations of what the current best facilities can see compared to what we expect to be able to see with the SKA.
So how do we get from this, giant telescopes, to torrents of data? Well, the journey from a photon to an exabyte starts here. Radio waves emitted by objects in the universe reach the Earth and our telescopes, bouncing off the dishes and landing on the receivers. Put simply, radio waves induce voltages in the antennas and receivers that capture them. and modern technology allows us to digitize these voltages to higher precision than ever before.
From there, optical fibers transport the digitized data from the telescopes to what we call central processing facilities, or CPFs for short. We'll have a total of 100,000 kilometers of dedicated fiber within the observatory. That's enough to stretch a quarter of the way to the moon, and it will carry 8 terabits per second of data from the antennas at the 2 sites into the central processing facilities. There's actually one of these for each telescope, but they do the same job.
The CPF is where the signals are combined together using FPGAs and GPUs, and actually including some exciting CPU, GPU, FPGA hybrids as well. And it's where the data becomes information. But to do that successfully, we must first synchronize the data to make sure that it enters the processing chain exactly when it should. This is to account for the fact that our radio signal from space reached one antenna before reaching another. We need to correct that phase offset so we can combine our signals. And since we know the exact time the signal was received, down to the nanosecond, we can do that. Once we've done that, we apply a Fourier transform equation, written here.
It looks complicated, doesn't it? And the Fourier transform is extremely useful because it decomposes essentially a function of time into the frequencies that make it up. It moves us into the frequency domain. In fact, we can do this operation with such precision that the SKA will be able to distinguish across its receiving bandwidth 65,000 different radio frequencies simultaneously. This is definitely big data. Over to you.
Once the signals have been separated in frequency, there are 2 ways that we can then process them, which depend on what we're looking for. We can either stack the signals together from the various antennas for what we call time domain data. Now, each stacking operation corresponds to a different direction on the sky. We'll be able to look in 2,000 such directions across both telescopes simultaneously. This time domain processing allows us to detect repeating objects such as pulsars or one-off events like gamma ray explosions and fast radio bursts. Excitingly, if we do find a transient event, we're planning to store the raw voltage signals at the antennas for a few minutes so we can go back in time and investigate them to see what happened. And it's the time domain processing that allows us to measure pulsar signal arrival times accurately and detect a drift if there is one as a gravitational wave passes through. But we can also use these radio signals to make images of the sky. And to do that, we take the signals from each pair of antennas, each baseline, and effectively multiply them together, generating data objects that we call visibilities. You can see this being done here for a few signals, but imagine it will be done for 200 dishes and 512 groups of antennas. That's 150,000 baselines and 65,000 different frequencies. That makes up to 10 billion different data streams. Doing this is a data-intensive process that requires around 50 petaflops of dedicated digital signal processing power.
So the signals are processed inside these central processing facilities in the way that depends on the science that we want to do with them. Once they have been processed, the data are then sent off on more fiber optic cables to our science data processors, or SDPs. There will be 2 of these great supercomputers, one in Cape Town in South Africa for our dish array, and one in Perth in Western Australia for our low-frequency antennas. As previously, as Rosie has just indicated, we have 2 flavors of data within the science data processor. In the time domain, we'll do work panning for astrophysical gold. We'll be searching over 1.5 million candidate objects every 10 minutes, sniffing out the real astrophysical phenomena such as pulsar signals appearing or single flashes of radio light. That 10,000 to 1 negative to positive imbalance is going to be a real challenge for the machine learning that is implemented.
But the greatest computing burden that the science data processors face is to take those incoming 10 billion visibility data streams and to make sense of them. And this is really hard. Why? Because inside the visibilities, the image of the sky and the antenna responses themselves are all jumbled up together, as you can see in this intimidating equation. Now, this is your second piece of homework, guys. So the I in this equation is the sky. That's the kind of truth that we're looking for in our experiments. And the A's here are the different antenna responses for each antenna. So we need to do another massive Fourier transform to get from the visibility space that depends on the antenna separations, which are the U's and the V's in the equation, and get into the sky plane, which is represented by the L's and the M's. Ultimately, we need to develop self-consistent models, not only of the sky that generated the signals, but also of how each antenna was behaving, and even how the atmosphere was changing during the data gathering. And we can't do that in one fell swoop. Instead, we'll have several iterations trying to find an agreed set of calibration parameters and source positions and brightnesses. With each iteration, as we improve our understanding of the system and the sky bit by bit, fainter and fainter radio sources emerge from the noise, as you can see happening behind me here for a couple of fields in the sky. So every time we do another iteration, we apply different calibration techniques and we improve our model. The trouble is we can't be sure exactly when this process will converge, so it's going to be difficult.
Rosie, these people don't want to be told that it's difficult. They're used to difficult. But how about telling them how difficult it's going to be?
Well, OK. A typical SKA map will probably contain hundreds of thousands of radio sources. Our iterative calibration and imaging process will use data flow programming with 400 million points on the graph. The incoming data sets are about 10 petabytes in size, and our output 3D images are 50,000 pixels on each axis. That's 1,000 desktop hard drives, 1 petabyte per 3D image. In total, the processing that we need in the SKA science data processors is about 250 petaflops peak. There'll be 200 petabytes per second of aggregate bandwidth to fast working memory, and about 80 petabytes of storage. We need between 0.5 to 1 terabyte per second of sustained write to storage, with sustained read rates 10 times higher. So this is real-time, responsive, high-performance data analytics. And to make it harder, we need to operate day in, day out. The science data processors are an integral part of the SKA telescopes. If they fall over, the telescope will have to stop observing, or at best to reschedule. So we're constantly trying to keep up with the data pouring in from the receivers.
So once the data products leave the science data processors in South Africa and Australia, they will be distributed, probably on dedicated fiber, to SKA regional centers around the globe. And every year we'll be distributing, once we're fully operational, up to 700 petabytes of data. Now, scientists won't be able to download these data products, let alone process them on their home computers or even their university network, because they will not be bite-sized, but they're going to be petabyte-sized. So what will they do instead? And this is another real game changer that the SKA, CERN, and other facilities are bringing about. They will use the computing power of the SKA regional centers pooled together to analyze these data products for them. And this reliance on a truly connected HPC world is one of the reasons why SKA's challenges resonate so well with the conference theme this year.
These scientists typically work in teams of experts, from half a dozen to many dozens or even hundreds, spread across the globe, and they collectively develop their understanding of the parts of the puzzle of the universe. The SKA regional centers will be federated, and this federation and interconnection will enable the science teams to collaborate easily and effectively, testing and retesting their analysis pipelines, predicting the results from theory or tweaking their theories to better match the results, and comparing the radio data with data from other parts of the electromagnetic spectrum. Users from around the globe will be able to explore the data in new ways and hopefully unearth new scientific discoveries. SKA is not just a machine for a few hundred expert radio astronomers of today, but for many thousands of astronomers, professional and amateur, and data scientists too, for decades to come, some of whom will work in scientific fields that are yet to be discovered. By being as inclusive as possible and upholding the best in scientific methodology, the information that SKA generates will really become knowledge and eventually wisdom.
Wisdom is connected knowledge, our global collective understanding of the meaning of the discoveries we've made and what they say of the human condition and our place in the universe. So although SKA isn't exactly easy, I hope you'll agree that it's worth a little extra homework.
Thank you.
All right. Wow, I was so excited I threw down my microphone, sorry. Thank you very much, Rosie and Phil, for this very exciting talk. And I'm sure we have a few questions we want to ask the people. So we have microphones in the row, and so please line up. There's microphones, please line up at the microphones, and then I will call you. So while the people are lining up, perhaps like one quick question. So, I mean, you're starting already, but do you see already impacts the project's making to science?
Sure. I mean, within the design consortia, the universities, the institutes, the industries that are already developing the technologies, we're already seeing positive spin-offs arising from that work in a variety of different areas. In imaging algorithms, in data compression techniques, and low noise amplifiers, many other areas. So yes, we're seeing those impacts, and it's one of those things that governments are very interested in seeing what the societal benefits of investment in such facilities might be. Okay.
So the first person on microphone number 2, please quickly say your name and organization and then the question.
My name is Rafi Moore. I'm from Israel. The name of the company is Raphael, similar to my name. My question is, both sides of the SKA is on the south part of the globe, so that allows you to see only half of the universe. Is the reason for this scientific or practical?
Well, that is quite a good question, actually. So it's true that from the southern hemisphere, you can't see quite all of the northern hemisphere. However, you can see the same hemisphere of the sky as the other state-of-the-art telescopes in different wave bands. So it's quite important that SKA is seeing the same sky as ALMA and as the large optical telescopes as well. Of course, we would hope that the universe is pretty much statistically the same in the northern hemisphere and in the southern hemisphere. If not, then there's a big controversy, a conspiracy against us and we're in trouble, but hopefully it shouldn't matter. The southern hemisphere gives us much better access to the galactic center as well, so that's very helpful for studying the pulsars that I mentioned, for the gravitational wave work.
Good. Microphone number 3.
Michel Müller from Tokyo Institute of Technology. I'm wondering about Sagittarius A star, the central black hole. Let's assume you are in full operation and there would be a gas cloud near or falling into that black hole. Do you have a guess at the resolution that you can get, like, let's say in terms of light hours or light years?
I can tackle that one. So it's an excellent question, and we pray for a gas cloud falling into Sagittarius A star, the supermassive black hole in the center of our galaxy, once we're operational.
Not before.
SKA itself will not have the resolution to actually distinguish what will be happening down there. That's the spatial resolution. Our telescopes, although ultimately spread over 3,500 kilometers in Africa, will still not have the resolution to pick out the appropriate details. However, there is an experiment currently underway using the world's millimeter telescope. So at 7, 3, and 2 millimeters, spread across the whole globe, and that will have the resolution at the appropriate frequency to be able to study this phenomena in the center of the galaxy. So yeah, it will be complementary to that. We'll provide the bigger picture to that detail.
Yeah. Number 1.
Hi, my name is Stephen Brandt. I'm from Louisiana State University. You talked about the possibility for detecting radio signals from other worlds, SETI type thing. You touched on it. I was wondering if you could give us more of an idea of the numbers, like how far away and so on.
Well, I can't off the top of my head.
Oh, okay, I can take that one as well. So with our current facilities, such as the big single dishes you saw, we could detect a mobile phone signal across our solar system. With SKA phase 1, we should be able to detect, if they exist, airport radars out to about 50 light years. And there are thousands of stars within that 50 light years. With the full SKA, when we have the full collecting area, we should be able to detect TV signals, again, if they exist, from the nearest tens, maybe 100 stars. But we'll be able to detect the airport radars across the entire galaxy. So that gives you an idea of what the capability is. Of course, it does rely on ET being out there and generating like we do.
Yeah.
Thanks. Microphone 2.
My name is Juliet. I'm a postdoc at Lawrence Berkeley Lab. My question is, with the installation of so many telescopes, have you looked at the impact on the environment of those material in the natural environment?
Again, that's probably one for me, Rosie. Absolutely, we have. And in fact, in both countries, we are currently engaged in not only environmental surveys, but the geotechnical surveys, and heritage surveys, working very closely with the indigenous populations to make sure that we are as sensitive as we possibly can be to those local environments. We have a very strict environmental policy within SKA. You know, our intent is to do no harm to the land on which we sit. And in fact, you saw an example also of us using renewable energy, and that is our intent. We don't want to be taking truckloads of diesel out to these beautiful areas of the globe. So no, we're extremely conscious of all of that, and I hope we're putting all of the right processes in place.
Okay, number 3.
Hi, I'm José Moreira from IBM. I want to ask about the, let's see if I got my terms right. You have the raw signals from the antennas that get processed in the DSP facilities to produce the visibility streams that go to the science processor, right? Do you need and do you have the ability to save some of the raw data until the science processor processes something? You can go back and change the DSP so you didn't miss something when you formed the visibility stream?
Yes and no. So, yeah, we will save a few minutes worth of the very raw voltage data at the antennas, but that's more to do with finding transient objects, which might be found in the image domain as well. If you find such an object, you can go and dump the raw data out of the antennas, but there's not really a plan that you would then send it back through to remake the visibilities. You would just collect the raw data and take it elsewhere to analyze offline. But a really nice thing that happens in the science data processor is that because we'll run the main imaging and calibration, the iterative pipeline will run kind of in pseudo real time. So it'll actually be buffered and offset so we can do load balancing. And that means that if we find an event happen, we'll have that buffered, 6 hours or so worth of data, and we can change which algorithms, with the parameters we run for pipelines on those, and choose if we want to keep the raw visibility data. What we can't do is go back and remake the visibilities themselves in the CSP, unfortunately, at the moment. But give us more compute, and we'll always do more stuff with it.
Thank you. The last question, number 1.
Okay, thank you. Hello, my name is Cameron Smith from Rensselaer Polytechnic Institute in upstate New York. So I have a non-technical question. As I understand, the United States isn't a full member of this project. If so, why not?
That's a good question.
Well, actually, when Bernd invited us to come and give this talk, I thought this is an opportunity. Look, the US was a major player in the SKA. In fact, much of the original concepts and the design work came from collaborations involving US scientists and astronomers. it was in 2010, 2011 that due to various budgetary pressures, the US decided to drop out of the project at that stage. But we are looking for every opportunity for the US to rejoin. And in fact, I even joke that if the US was to provide, say, $2 billion, we would change the spelling of kilometer so you guys would feel more comfortable with it.
So that's unfortunately all the time we have for questions, but the SKA project actually has an exhibition booth up on the exhibition floor. It's booth number 228, and people from the SKA people will be there all week. So if you want to see how your company gets engaged or you have further questions, please visit them at booth 228.
Yep.
Thank you again. And have a great week. Have fun. Thank you, guys.
Behind your eyes, holding on to, and I am waiting. Oh, my love is getting tired. We were young back when we started, getting further, and I'm still waiting. Oh.